Hello one and all, and welcome to the Math Magic Show. In this one, let's take a look at finding the following limit. So we have here, as x approaches a, of the root of a minus the square root of x over a minus x. That's our limit here. Now, let's recognize a basic issue with this limit. There's an issue which looks like this. When you try to place x with a directly, so a in yellow is the value that I'm approaching right here. You see that? So when I try to replace x with a directly, there's a problem, which is, look, on the bottom, when I carry this out, I have the following, that I have 0 over 0, because a minus a is 0, and the root of a minus the root of a is 0 on the top. The 0 on the top is not the problem. The one on the bottom is the problem, because that is what leads to division by 0, you see? So we can't just plug, in other words, replace x with a directly in this expression. We have to take some additional steps. So something that you can do, as an example, is the following. Take a look. You could rewrite the expression on the bottom as follows. Instead of writing just a in this position, what you can do is write the following. Write the square root of a squared, and the reason for that is that the square root and the 2 would cancel off and it would give you back that original a in that position, you see? Same thing with the x over here. You see, I can write that as the square root of x and the quantity squared, and the reason is that the 2 here and the root will cancel and will give back the original x in the bottom of the fraction. There's a benefit to this. Take a look at the benefit of knowing how to write an expression that way. The next step across the top, this expression on the bottom here that says the root of a squared minus the root of x squared, you can factor that as a difference of two squares. So in other words, you see on the bottom now it becomes the root of a minus the root of x multiplying the root of a plus the root of x. It's a difference of two squares. And that's useful because now take a look. You see on the bottom we have the root of a minus the root of x, and across the top from the original question we have the root of a minus the root of x. So you have the same quantity, which you can just cancel off. So this is what I mean. Take a look. Basically, those two can be stricken away. And I specifically put this times 1 here in that position just to remind you that there's no such thing as just canceling. Everything is multiplied by positive 1. And sometimes seeing that positive 1 you're multiplying by is really key to everything, to making sure that things work out correctly. So I'm going to cancel that off, and then at the next stage, let's see, this is going to give me the following. The limit as x approaches a of 1 over the square root of a plus the square root of x. Why is this expression better than the original? That's a good question always to ask. Why is one thing better than another thing? So here, this is better in the sense that we can replace x with a directly. This is what I mean. Take a look. You see, now I can simply replace this x with the a here that I'm approaching, and it's going to give me 1 over the root of a plus the root of a, which after simplification simply becomes 1 over 2 times the square root of a. And that is the value of the limit for given a's. So for example, if a were just 1, back across the top over here, imagine that a has the value 1. In other words, x approaches 1. Okay? Then the value of the limit would be 1 over 2 times the square root of 1, which is 1, so it would be, in other words, 1 over 2, and so on. I hope this has also convinced you the fact that it's better to work with letters a lot more. Yes, it's helpful to first do some numerical examples, but then you want to look at the numerical examples and learn how to extract the essential ideas from the numerical examples and work with, for example, variables and parameters more than just always numbers. Because the underlying concept is the same as it would be in the case of numbers, but what you develop often at the end is something like, for example, this last step here. It's kind of a formula, essentially, that works in many cases, and not just for a specific value of a, like 5 or 10 or 1. And that is it for me. Thank you so much for watching. Please leave a like and subscribe, and I'll see you in another video.